Okay, so let's look at the thermodynamic limit. So previously, what we saw was that we derived so far the second law, right? From the principle of statistical mechanics and the microcanonical ensemble. Okay, based on and we also just derived the 0th law. We took a stab at the definition of temperature, and we saw that definition of temperature, along with the idea that the maximization of entropy leads us to the physical configuration, gave us these two laws, right? So how justified are we in assuming that what we are calling the most probable configuration? It is most probable because it maximizes the entropy, right? So it has the most number of states. That configuration comes out of the most number of possible microstates. So how can we say most probable is equal to what is physically realized, right? So usually in statistics, when we have an average, averages mean that there are some uncertainties, right? So if I give you a probability for something, it means that it's not going to happen. So how can we say that most probable is the physical? So what I'm going to argue in today's lecture is that when the system size is large, that is the number of particles go to infinity, or say 10 to the power 23, which is quite large, almost infinite. This is the limit called the thermodynamic limit. And in that limit, the relative broadening of the probability is 0. Okay, it goes to 0 very rapidly. So let's do that in the context of an example. And the example that we're going to look at, it's the thermodynamic limit of a monoatomic gas or monatomic gas. So a monatomic ideal gas is the simplest kind of gas that we can think about. Now, you can show, and this is not something I'm showing right now because it'll involve taking a detour into classical mechanics, into phase spaces. How many of you know about phase spaces? Like, I think only those. Okay, but it's usually.
I took physics too, of course. Yeah.
Right. Does everyone know? I mean, I think some of you haven't seen phase space, right?
So is this the same as the complex numbers phase space?
No, it's not. So it's a space the of the position and momentum of a particle, the generalized coordinate and the generalized momentum. So anyway, so let me not go into that. But a very fundamental, analysis of the motion of the monatomic ideal gas tells us that the number of states with energy E is roughly given by some constant that doesn't concern us times e to the power 3. N is the number of atoms divided by 2. Okay? Where C is some constant. So we just start this as an assumption, and let's bring two monatomic gases together, and then we know that the number of configuration of the combined system will be given by omega 1 E1 times omega 2 E minus E1, right? So according to our, microcanonical ensemble, the probability that of E, the first gas having energy E1, and let's just take its log. Before we take the log, let me just, the probability will be just, this thing, 1 divided by omega 1, omega 2. So if I take the log of this, the nice thing about log is that log is it's a monotonic map, right? So if I find that if I extremize a log of a function, the point of the extrema is also going to be the extrema of the function itself. So the log of this thing is going to be some minus some constant plus 3n1 by 2 log of E1 plus 3n2 by 2 log of E2. Okay. So, we want to get the most probable configuration, which is given by this. And that leads us to the condition that, we can drop the 3's, that N1 over E1 must be equal to N2 over E2. And let me denote the extreme values by tildes. Okay, so this is the condition that we get from here. Okay. So this is the most probable value of the energy, E1 and E2. So we can identify that to the internal energy of the system. Okay. So, the entropy of system 1 with internal energy U1 is Kb log of omega U1, right? So what is 1 over the temperature times Kb? Well, it'll be 1 over Kb times del S1 divided by del U1. And if I now, put in the expression for omega here, we are going to get del by del U1 log of C1 U1 3 by 2 N1. Of course, the constant part drops out of the derivative, and therefore we end up with 3 by 2 N1, and the derivative of log of U1 is 1 over U1, right? So from here, we find the expression that the internal energy is 3/2 of N kBT. Okay, something we expected anyway. And so what we can say is that, the expression that N1 over U1 equals to N2 over U2, then leads us to using this expression for U, 1 over Kb T1 is equal to 3/2 N1 U1. And so this is the left-hand side. And from the right-hand side, I can write this as Kb T2 3/2 N2 U2. So this means that T1 is equal to T2 is equal to T. Something we already knew, right? But I'm just like deriving it slightly more rigorously here. And then, let's look at the second derivative of the probability. So the second derivative, if you work this out, it's going to give you, and let's look at it at maximum. When it is at maximum, then we can set T1 equals to T2, and then we get 2/3 by KB squared N1 T squared minus 2/3 1 over KB squared N2 T squared. And if I combine these two things, I get minus 2/3 1 over KB squared T. There's a T squared. And then over here, I get N1 plus N2 is N1, N2. And because it's a maximum, this has to be less than 0. So this is at the maximum of the second derivative. Now what we can do is that we can expand our probability function around the maximum value. So we are going to get some constant, and then we're going to...
আমার একটা প্রশ্ন ছিল, সো ওইখানে যে লাইক লেস দেন 0 হচ্ছে, এটা তো এমনিতেই বোঝা যাচ্ছে না, লাইক অল দ্য টার্মস আর পজিটিভ হিয়ার, রাইট?
Yeah, exactly. Yeah.
আচ্ছা।
Yeah, it's trivially true. Yeah. So so what we are doing now is that we're expanding the probability as a power series around this maximum. So the first derivative term is going to be 0, right? So the first derivative term is 0, and the second derivative term, it's going to have a factor of half, because that's what we get from the Taylor series expansion, and then minus 2/3. I've written the minus here, and this thing, 1 over KB squared T squared N1 plus N2 divided by N1, N2 times, E1 minus the value at the maximum, 3/2 N1 KBT squared, right? And then the higher order term. So now if I take this approximation, if I approximate my probability distribution up to this term, then we get what we are going to call a Gaussian probability distribution. So the Gaussian probability distribution, it will be some constant, say C tilde, e to the power, now these two is cancelled, e to the power minus 1/3 N1 plus N2 divided by N1, N2. And then E1 minus 3/2 N1 KBT squared. I think I'm missing a factor here. I'm missing this factor, okay? Yeah, I think I'm missing this factor. So there should be a factor of KB squared T squared, okay? Now, this is a Gaussian in E, right? So if I plot this Gaussian, so x-axis would be E1 and the y-axis would be P. Yeah, we are missing this factor because this is not dimensionless. To make the argument of the Gaussian, we need this thing. So the Gaussian is going to be something like this. we'll see that it's actually much narrower than this. And what would be the value of E over here? Can someone tell me?
3/2 N1 kBT.
Right. 3/2 N1 kBT. It's this thing, right? Because whenever you have a Gaussian, probability distribution, C is a normalization constant, and E is e to the power minus x minus a whole squared by b. The center of the Gaussian is this point, okay? And 1 over b is related to the width of the Gaussian. So without
will we
even
find the variance to be like tends to 0, something like that? This Gaussian.
Yes, that is the punchline. Yes, exactly. That is the punchline. So, so even without doing any calculation, we can we know that well because we have done this calculation before for Gaussians, that the expectation value of the energy is this thing, right? And this probably has some it's the name of some theorem, right? And
equipartition theorem.
then
Partition.
exactly, yeah. And then what is the width of E? Which is the width of E is going to be in the Gaussian approximation. It'll be, E. So this is all. I'm not going to write G. This will be this minus this, right? And this is going to be KB squared, T squared, and that N1, N2 by N1 plus N2. And then the relative error, so the relative error, which is a dimensionless quantity, and that's really what we want, is going to be the delta E divided by E1. And, I'm going to just like don't care about any of the prefactors. And this is just going to be, in the square root, it'll be N1, N2 divided by N1 plus N2, 1 over N1 squared, which is going to be proportional to N2 divided by N1 times N1 plus N2. And there'll be a square root, which I forgot here. So, in the N1, N2, going to infinity limit, this thing, the relative width, the relative error goes to 0, right? But if you take if you take N1 and N2 to be systems which has 10 to the power 23 particles, then the relative error will go to like 10 to the power minus 12 or 10 to the power minus 13, right? Which is, pretty small. So this is the justification that in the thermodynamic limit, what are we calling physically realized, what is physical is equal to the most probable, right?